Hi. In this video, we are going to continue our discussion of orthogonality, focusing on ideas of projections and how that leads to a least squares approximate solution to inconsistent systems. Let's begin our discussion with some introduction to the idea of projections. And we'll begin with the projection of a vector onto a vector, where things are fairly easy to understand. Given a pair of vectors, some u shown here and some v shown here, we can always write or decompose u into a sum, a unique sum, of one vector that is parallel to v and one vector that is orthogonal to v. This is shown in the picture here. There is a vector that is in the same direction as v, and a second vector that is orthogonal to v, and together their sum is gives us u. It's unique because if we took any different length of the parallel piece, we would not have a orthogonal connecting piece to give us u. So we can write this as u is broken down into a parallel piece plus an orthogonal piece, or parallel component, orthogonal component. Of course, the parallel component must be some scalar multiple of v. That's what it means to be parallel. And the dot product of v and the orthogonal component must be 0, which is what it means to be orthogonal. We give special name to the parallel component, and this parallel component we call the projection of u onto v. And we use the notation shown here, projection subscript v, to show what are we projecting onto, and u, what is the vector that we are projecting. It's important to note that this is not symmetric. The projection is not symmetric in any way. The projection of onto v of u, the projection of u onto v, does not equal the projection of v onto u. And this is perhaps obvious if you just think about the directions of things. The projection of u onto v must be parallel to v. The projection of v onto u must be parallel to u. They point in different directions. We don't typically give a special name to the orthogonal component, but the orthogonal component can be derived from this projection as the difference of u and the projection. And of course, then if we take this orthogonal component and add the projection, we get back u. So this is what we mean by the projection of a vector onto some other vector. It is the component of that vector in the direction of the target, where the other component is purely orthogonal to the component. This is a conceptual definition. How do we actually find or compute the projection? Well, we just have to put together all of the pieces that we already have defined, and we will derive a nice, clean method to do so. We've already noted that the projection must be a scalar multiple of v, because it's in the same direction as v. Also, v transpose, so the dot product of v with the orthogonal component, u minus the projection, must be 0. We write this as v transpose, u minus the projection of u onto v is 0. And if we substitute in kv for this projection piece, gives us v transpose u minus kv equals 0. We can multiply the v transpose through, and move one of the pieces to the other side, and we get an equivalency here that V transpose U must equal K times V transpose V. This can, of course, be rearranged to give us what this constant is. The constant is the ratio of V transpose U over V transpose V, the dot product of V with U over the dot product of V with itself. And the projection is simply that scaling factor multiplied by V, or a final formula written down here. Okay, so we've defined what it means to be a projection of a vector onto another vector and come up with a way to compute it. I should note that although this diagram might look like it's in 2 dimensions because it's on the screen, nothing that we did here was dependent on this being in 2 dimensions. This result works in any number of dimensions. Okay, now let's move forward to the idea of a projection onto a vector space. We're going to use many of the same ideas. Given a vector U and a vector space V, we can similarly, so here I have a vector space represented by this plane. I'm showing this as a 2-dimensional vector space because it's easy to draw. The ideas extend to higher dimensional vector spaces. So we have some vector space that maybe has 2 basis vectors, a spanning set, V1 and V2. And a vector U that is perhaps not in that vector space. It does not lie on the plane, it lies off of the plane. We can always write U again as a unique sum or a unique decomposition into a vector that is in U, that we will call the parallel component, a vector that lies in the plane, and a vector that is orthogonal to the plane, an orthogonal component. That is, this vector orthogonal component has to be orthogonal to every vector on the plane, including the component that is in there. This is unique for the same reasons why the projection of or this decomposition for a vector onto another vector is unique, that if we move this component of the plane to somewhere else, we would no longer have a right angle when we move up to complete U. So we have a parallel component and an orthogonal component, just as we had for the projection of a vector onto a vector, but the component that is parallel to a vector space rather than just a line. We can characterize this in the same way. The parallel component has to be an element of the vector space V. It has to be part of V. That's what we mean to be in a vector space. And the dot product of V transpose and the orthogonal component has to be 0 for every vector in V, what it means to be orthogonal to a vector space. We are going to give the same meaning to the concept of a projection, the parallel component of this sort of a decomposition. The projection of a vector U onto a vector space V is simply this parallel component in a decomposition into a parallel and orthogonal component. Right? We can think of this as this is the part of U, the component of U that lies in the vector space when we break it down into a parallel and orthogonal component. Of course, the orthogonal component, once again, is simply the difference of U and this projection. We form a triangle that looks exactly the same as our triangle we looked at before. Okay, this is our conceptual definition. Once again, let's see if we can derive a way to compute the projection. This is going to be a little bit more involved, but is going to make use of exactly the same ideas. So To simplify our discussion, I'm going to collect these two basis vectors. Remember that when we talk about vector spaces, one of the ways we can describe them is with a basis, a set of linearly independent vectors that span the space. So if V is the span of these two linearly independent basis vectors, and just to collect these, let me place these vectors as the columns of a matrix A. Okay. Once we've done that, what are some of the rules that we have? Well, we know that this difference, U minus projection of U onto the vector space V, must be orthogonal to all of the vectors in the vector space, and it's sufficient for orthogonality to a vector space to look at orthogonality to the basis vectors. So we can require that V1 transpose times this orthogonal component and V2 transpose times that orthogonal component both equal 0. We're taking a row vector multiplied by a column, a row vector by the same column. We can combine these into a single expression, A transpose times this same orthogonal component, and this has to equal the 0 vector. Okay, one of our pieces, orthogonality. The second piece we need is that the projection of U onto V has to be part of this vector space, part of the span of these. Well, by collecting these two vectors as columns of the matrix A, this span, this linear span of V1, V2, is the column space of that matrix. So we can say that the projection, the piece that lies in V, must be part of the column space. Why is this helpful? Because we know what a column space means. A column space of a matrix is the set of right-hand sides that have a solution. If the projection of U onto V is part of the column space, then there must be some vector W. We don't know what it is, but we know that it exists, such that A times W equals this projection. That is, the projection is a valid right-hand side for AW equals B. So again, I don't know what W is, but I know that it exists. Since we know that it exists, we can make the same sort of substitution that we made before. I'm going to take this orthogonality equation, A transpose times U minus the projection of U onto V equals 0, and substitute in the projection piece for A times W. This gives us A transpose U minus AW. Multiply the transpose through, and in the same way we did in the last case, take the two components of that and put them on either sides of the equality. Gives us A transpose U equals A transpose A times W. Now, I'm going to be moving forward making an assumption, but one that holds true as long as we have a basis. Let me briefly explain where this is coming from. In this example here, A was a 2 by n matrix. I don't know, I've diagrammed this here. Maybe you can think of this as being in three-dimensional space, but it doesn't have to be. V1 and V2 could be vectors of really any length, but I have them set up. I have two of them, so I know that it's not a 2 by n, m by 2 matrix, right? M rows and 2 columns. A transpose, of course, will be then a 2 by m, and this A transpose A will be a 2 by 2 matrix. As long as these columns are linearly independent, then the rank of A is 2, the rank of A transpose is 2, and what we will end up with when we multiply this 2 by m and m by 2 matrix will give us a 2 by 2 matrix square that ends up being rank 2, non-singular. This small square matrix is a non-singular matrix that we can invert. Because we can invert it, we can isolate W. We can solve for W by multiplying both sides of this by the inverse of A transpose A. And this gives us W, A transpose A inverse, multiplied by A transpose, multiplied by U. Then substituting in the fact that we knew that W was the solution to this AW equals projection of V, this gives us a result for the projection of U onto V. A from here multiplied by A transpose A inverse multiplied by A transpose times U. Now, if we think about this formula, A simply contains the vectors V, U contains the vector we're projecting onto. These are things that we must know in order to find the projection. What is U and how do we describe V? That's all we need. Okay. This might look a little bit weird. We're taking a product of what it seems to be the same matrix over and over again in different forms. Nothing does cancel out in here. We have to leave this in its whole. This actually has some deep relationships to what we saw in the previous case. Right? Let's summarize where we are now. In order to find the projection of U onto a vector space V, all we need to do is define a matrix A whose columns are a basis for V. I showed it for the 2 by 2 case, but nothing that we really defined there wouldn't extend perfectly well to higher numbers, higher dimensionality vector spaces. So we define a matrix A whose columns are a basis for V. When we've done that, we can then simply compute the projection of U onto V with this general formula. If we take a look at this and we compare this to the projection of a vector onto a vector, that first result ends up just being a special case of this, which it should. The projection of a vector onto another vector, we can consider that vector as being a one-dimensional vector space, or the basis for a one-dimensional vector space. And the result we had for that we had written as the ratio of V transpose U over V transpose V times V, has all of these times V, has all of these same components. This 1 over V transpose V can be written as V transpose V inverse, equivalent to A transpose A inverse. This ratio is simply a scalar, and so we can move this vector we can either leave it on this side or we can move it to the other side. Moving it to the other side puts a vector V here, equivalent to the A in this position. What are we left with in this numerator, V transpose times U? This is equivalent, this V transpose times U piece that is here is equivalent to A transpose U. In the case of a projection of a vector onto a vector, these dot products are scalars, and so we can move them around. We don't have to worry about the order. In the case of the projection of a vector onto a vector space, we have matrices and matrix products. We are not free to move those around because matrix multiplication is not commutative. So we have this general case for a projection. Now that we've defined how to calculate projections and given a little bit of a conceptual understanding of what it is, let's talk a little bit more about what the projection might mean. And this is going to have a relevance to how we use the projection to solve problems. So we have this U. We've taken a projection down into V that we can represent by this triangle, and we have this orthogonal component. We mentioned that one of the ways we know this is unique is that if we move this projection arrow and we tried to define it in a different way and to write a new linear combination of vectors to give U, we wouldn't have this orthogonal component orthogonal. That new component would also be longer. Right? If we try to move this around so that the triangle no longer makes a right angle here, this component will always get bigger. Right? You can think about this as if you think about what is the shortest distance from a point to a plane, that shortest distance from a point to a plane is always the distance that ends up always along the line that ends up being orthogonal to the plane. Right. So we can think of another way of thinking about the projection is as the point that is in the vector space, the single point in the vector space V, that is closest to U, and closest in the sense of a Euclidean distance, the norm of a vector, the vector in V that has the smallest length when we compute the difference U minus V. The closest point to U in V. The orthogonal component is then the deviation of U from that closest point. It tells us how far away that point is from the vector space using the shortest distance as the measure. These ideas are going to have relevance for what we are going to discuss next. Okay. We have discussed a lot about solving linear systems. We've discussed how to solve it just using Gaussian elimination, how to compute matrix inverses to solve non-singular systems with multiple right-hand sides, how to use LU decomposition to solve for multiple right-hand sides when we have singular or non-square matrices. But everything that we have done so far, we've still sometimes come across inconsistent systems. When the echelon form of a coefficient matrix includes 0 rows, some right-hand sides have no solutions. Right? We can describe this in a few different ways. We can say AX equals B. If B is not in the column space of A, then this has no solution. We can also just define this more operationally. If we start with an augmented matrix and we carry through Gaussian elimination to an echelon form, if the echelon form of U has a 0 row and C has a non-zero entry in that position, we can think of that as the rank of UC, that C has this augmented matrix has kind of an extra pivot. Well, it's not a pivot, it's not really a true pivot in the sense of the coefficient matrix. The rank of this matrix is greater than the rank of U. We have a non-zero entry in C where U purely had zeros. And so far what we've done is every case that we've had no solution, we've simply said there's no solution. We don't really know what to do here. That's not a very satisfying result. In many real-world applications, you might end up with a problem that doesn't have a solution. You don't just want to throw up your hands and say there's nothing to do. Can we find an approximate solution? Way back at the very beginning of the class, when we were defining what linear systems were like, we considered this idea and explored how guessing and testing in a making successive estimates and then reevaluating and making a new guess and a new evaluation might be able to find such a solution. But that's a very tedious way, a very error-prone way, and a method that is in no way guaranteed to actually work. A well-defined way to get an approximate solution, right? This isn't the only way, but a well-defined way to get an approximate solution might be to say, let's find the solution that gives a right-hand side as close as possible to b. Ax equals b does not have a solution. Let's try to find a solution. Ax equals p, so p has to have a solution, in such a way that the difference between b and p is minimized in its absolute, in its Euclidean distance sense, in its norm sense. Right? All right. This might start looking familiar. We just saw in the context of a projection that the projection means, in some sense, a vector that has the minimum distance between two vectors. And so let's see where this idea takes us. Well, the right-hand side for the approximate solution must be in the column space. Right? By definition, we're saying let's find an x that has a solution in such a way that the difference between that solution and the desired right-hand side is minimized. That means this the test solution, if you will, p must have this test right-hand side must have a solution. P must be in the column space of A, right? Part of a vector space. Right? What we want then is a P that is closest to B, but in the column space. We've just seen what that is. The point that is closest to a vector B, that is in some vector space V, the column space of A, is simply the projection of B onto that vector space, the projection of B onto the column space. How do we find the minimum vector, the P that minimizes this distance, subject to P being in the column space? That is, P must be the projection of B onto the column space. And we know how to compute projections. So let's put this together. Given some inconsistent system, Ax equals B, the solution that yields a right-hand side as close as possible to B is given by that new right-hand side is given by the projection, and so we would get that by solving this equation, solving Ax equals the projection of B onto CA. As long as the columns of A are linearly independent, so if the columns of A are linearly independent, then they are a basis for the column space, and everything that we've discussed before would hold true. That is, the projection of B onto the column space would be given by our general result, which we can then substitute into this expression to give us Ax equals A times A transpose A inverse times A transpose B. We see on both sides of this equation we have an A, and especially again because we have linearly independent columns, this means that the null space of A is 0. This system has a unique solution, which means that unique solution can be found simply by canceling out these A's on either side. X equals A transpose A, all inverse, multiplied by A transpose B. You've noticed here that we haven't even needed to take any intermediate step of computing a projection. As long as the columns of A are linearly independent, we can directly find this solution. well-defined way to find an approximate solution for a linear system. We might take a look at this and see that this looks a little bit, conceptually anyways, like a inverse. Remember that in the case of a non-singular system, we had some ax equals b, and as long as A was a square non-singular system, we could rewrite this as x equals A inverse times b, some matrix that we multiply by the right-hand side to give us x. Here we have some matrix that we multiply by the right-hand side to give us x. It's a more complicated looking matrix, but there's a conceptual similarity. This similarity is actually quite deep and leads us to a really interesting definition. And it's the idea of a pseudo-inverse. The pseudo-inverse of a full column rank matrix. Everything that we've discussed here, what was necessary for the result that we mentioned before, what was necessary for our derivation of how we get the projection, was that the columns are linearly independent. This is necessary because if the columns are not linearly independent, this inverse does not exist. This A transpose A is no longer a non-singular matrix. But if the columns are linearly independent, this is the same thing as saying that A is full column rank. If A is an m by n matrix, the rank of A is n. There are n pivots, n linearly independent columns, no free variables. In this case of a full column rank matrix, we can define a pseudo-inverse that is simply this product that we were going to use, this matrix that we were going to use to multiply B by in order to give us an answer. And let's think a little bit about the properties of this product and why we might call it a pseudo-inverse. First of all, we can note that this A plus, and this is the notation we use, A superscript plus, is a left inverse. A plus A is A transpose A all inverse multiplied by A transpose A. Well, obviously this is A transpose A multiplied by its inverse must give us the identity matrix. It's a left inverse because when we multiply A plus on the left-hand side of A, we get the identity matrix. It is not a true inverse because if we do the other multiplication, A times A plus, this gives us A times A transpose A all inverse times A transpose. This is not something that we can simply, that gives us I. The order of multiplication matters here. We cannot, we don't get I in this case. Okay, so we call this a left inverse, but not a right inverse. For a non-singular matrix A, that is if A is full rank but is also square, then this A plus gives us back the inverse, the true inverse. A plus would be A inverse times A transpose inverse times A transpose. We get this by essentially propagating out this inverse through this product, which we can only do if the individual inverses exist. And then A transpose times A transpose inverse, of course, gives us the identity matrix, which leaves us only with A inverse. So when this definition gives us the inverse, when we have a square matrix that's full column rank, it is a left inverse for non-square matrices that are full column rank, and it lets us solve systems in a analogous way to the inverse, but for getting approximate solutions. And for these reasons, we call it a pseudo-inverse, a false inverse. It has some of the properties of a matrix inverse, but not all of them. Okay. This pseudo-inverse lets us organize everything in a really, really clean way. As long as we have a full column rank matrix, and I want to emphasize this only works when we have full column rank, right? No free variables. When we have a full column rank matrix, we can always define a pseudo-inverse, A plus A transpose A, all inverse times A transpose. And this pseudo-inverse will always give us the best answer, for a certain definition of best, for any right-hand side. Ax equals b can always be solved with x equals a plus b for any right-hand side, as long as A is full column rank. When there is an exact solution, this result will give us that solution. We know that the pseudo-inverse becomes the inverse when it is square and full rank. When it's non-square but full column rank and B is in the column space, the projection of B onto the column space just gives us back B, and so we get the same well-defined solution. So when there is an exact solution, this gives it to us. And when there is not an exact solution, this gives us the solution to Ax equals P that has the smallest error in the right-hand side. So one result can give us both the exact solution when one exists and the approximate solution when one doesn't exist. This might be worrying. How do you know when you're getting the exact solution and when you're getting an approximate solution? You can always assess this by computing what the error vector is. The error vector we define just to be this difference, b minus p. How far away was our real right-hand side from the right-hand side that we actually got a solution for? And it's given by b minus a pseudo-inverse times b. Okay? If this we get as error vector of 0, it means we had an exact solution. If we have an error vector that is close to 0, it means we have a good approximate solution. If we have an error vector that is far from 0, it tells us that we have an approximate solution, but maybe not a great one. This gives rise to a very important discussion point. It is important when we're talking about approximate solutions to think about the quality of that approximate solution. As long as we have a full column rank matrix, this pseudo-inverse will always give us an approximate answer, and a best approximate answer, where best is defined as minimizing the length of this error. We call this a least squares solution. Why? Because what is the length of this error? It's the sum of the squared differences. Basically, we take every element of our desired right-hand side B, every element of the actual sort of solved for right-hand side P. We take the difference of all of those elements, square that difference, and add them up. Call that the sum of the squared error, and we minimize the sum of the squared error. That's really quite a mouthful, and so we simplify that by calling it a least squares solution. However, just because we can get a best approximation for any right-hand side does not mean that that approximation is always a good approximation. There's lots of things that can make us question the quality of the approximation. The error might simply be large. We might look at this error vector and it is very large in magnitude or in relative terms, and that might worry us about the quality of the approximation. The approximate solution might violate real-world constraints. It's possible, for example, that we start with a right-hand side that is all well-behaved, maybe all positive values where they need to be positive values, but this projection onto the column space leads us into a right-hand side that had negative values. Then our approximate solution wouldn't be a good real-world solution. It also can sometimes be the case that this definition of best, minimizing the least squares error, may not actually be the best for the problem. This is often occurs when the different elements of our right-hand side have different units. We looked at an example in the exam, for instance, where some of the equations were expressed in terms of hours available by different types of workers, and another equation was a dollar value of plants for a restoration project. When you have that, when you have very different units, this minimizing the length of the vector, well, is treating every term identically. And when the units are different, that might not be appropriate. There are often ways that we can adjust a system to put it into consistent terms, maybe translate all of the values into a dollar equivalent, for example, or in other ways try to normalize the meaning, the magnitude of the various elements of the right-hand side so that the least squares solution is more appropriate. But these are all things to be concerned about. I am not going to expect you to really be concerned about these issues in this class. We're focused on the methods, how do we find the solution, but keep in the back of your mind that this is for real-world solutions. We really do have to think about this side of the problem. Okay. What happens when we don't have linearly independent columns? That is, what happens if we have a system AX equals B, where B is not in the column space? We have an inconsistent system. The general result still holds true, right? A solution that yields a right-hand side as close as possible to B might be given by solving for AX equals the projection of B onto the column space. This formulation is still well defined, but if the columns are linearly dependent, then we can't compute the projection in this same way. The rank of A would be less than n for an m by n matrix. The rank of A transpose A then also has to be less than n, but A transpose A is an n by n matrix. That means this matrix must be non-singular, it must be singular. If it's singular, we cannot compute this inverse. We don't have this method of computing the projection. We can't define a pseudo-inverse. We can't use that general approach. Does that mean that we can't solve this kind of problem? Not at all. When we have this sort of a system, if we have an inconsistent system of less than full column rank, we can still solve the problem by starting off with trying to find a basis for the column space. Let's define some A hat, which is a matrix that is derived by A by removing all of the free variable columns. Recall that a way to find a basis for the column space is through the casting out algorithm. Identify the free variables and remove those columns from the original matrix. When we do that, we can call that sort of matrix we're left with A hat. That matrix has columns that are a basis for the column space. The columns have to be linearly independent. The column space of A hat is the same as the column space of A, which means the projection of B onto the column space of A is the same as the projection of B onto the column space of A hat. But A hat is a well-defined full column rank matrix. Because of that, we can compute this projection using A hat with exactly the same formula, and then go through and solve the system. And it's a very important correction here. This should not be A hat there. It should be A hat there. Erase that pen. AX equals the projection of B onto CA, where this is now our projection right here, substituting in this. So this would require a multiple step process. First of all, finding a basis for the column space of A, finding A hat, then finding the projection, and after we've found the projection, solving the system of AX equals this projection. By construct, we were only needing to do this because A was less than full column rank. It had free variables. The solution to this system would have a general solution. It would have, there's a null space to AX, non-zero or non-trivial null space to AX, which means there's many solutions to this, many equivalent solutions. What we end up with in this case is a general approximate solution, an approximate solution that is described by one approximate solution plus the null space. This is quite complicated, a fairly involved process with multiple steps. I wanted to present it here to show that there is a well-defined method to solve these systems. We are not really going to be exploring these inconsistent systems of less than full column rank with these tools very much. Later in the class, really in the last section of the class, we will introduce the idea of the singular value decomposition, which gives a cleaner way to look at these kinds of systems. All right. In the last little bit of this video, I just want to highlight one very important example application of this process. The idea of polynomial regression, fitting data to a line. You've probably heard of linear regression, fitting data to a straight line. This is a generalization of this idea, fitting a set of data to any polynomial. It could be a straight line, it could be a quadratic equation, it could be a cubic equation, or so on. It works as follows. We imagine we have some set of data, which are all data points in 2 dimensions, pairs, x1, y1, and so on. We can think about each of these pairs being a point on the xy plane. A point here, a point here, a point here, a point here, and so on, right? And depending on the structure of these, perhaps we would like to try to fit these data to a quadratic, as an example. Not a very good fit as I've sketched this, but hopefully you get the idea. Right? A model for this data, right, if the fit was perfect, if we could perfectly fit the data with a quadratic model, what we would hope to satisfy is that for every one of these pairs, x, y, and x, that the y would be expressed as a polynomial, a0, a constant, plus a1 times the x variable plus a2 times the x variable squared, and so on to whatever degree. The linear fit only has the first two terms. The quadratic fit only has the first three terms, and so on. And a perfect fit would let this equation be perfectly true for every one of the data points. That almost never happens. We can represent exactly this same idea, the idea that we want to fit every one of these data points to this equation, with a matrix expression. Here, the y's become a vector of all of the y elements. The common piece in here, the thing that is in common to every single one of the expressions, are the constants, a, a1, a2, and so on. So this should be a n here, sorry. Let me correct that. Which means that we should represent that piece with a vector here. And the piece that is different in every equation is the xi's. Will be different in every equation. But they have the same general form. The first column always has a 1. The second column always has the linear term. The third column always has the quadratic term, and so on. And so we can express all of these in a matrix where we have 1s in the first column. The second column is all of the x variables just by themselves. The third column is all of the x variables squared, all of the x variables cubed, and so on. Probably should have put in some ellipses here to show that this sort of continues across until we get to our last term, the x term raised to the nth power. I'm writing this in a very general sense. A linear fit, this matrix would only have 2 columns. A quadratic fit, this matrix would only have 3 columns, and so on. In general, the number of data points is much, much bigger than the number of columns. We do a linear quadratic fit, for example, to hundreds of data points. Many rows, very few columns. This is a very, very highly overdetermined system. It is essentially never the case that this system has an exact solution. Right? It is also almost always the case that the columns are linearly independent. In fact, unless the x values are all exactly the same, these columns will always be linearly independent, which means we have an inconsistent system with linearly independent columns. We can use concepts of projections and pseudo-inverses to find a least squares solution. Starting with a set of data, we define a matrix whose columns are processed versions of the x variables. The first column is, so each of the columns is a column that has the variable raised to that column. This isn't quite right. I should write this as j minus 1 here, raised, oh, sorry, that is not, because I did actually, we're starting counting at 0 here, so we don't have to bother doing that. Each column, Cj, is given by xi to the j. When j is 0, this is xi to the 0, x2 to the 0, and so on. This gives us a columns of all 1s at the beginning. For j equals 1, this gives us the variables by themselves. For j equals 2, this gives us the variables squared, and so on, exactly as we saw. So we define this matrix, the processed x variables, with 1s in the first column. We define a y vector that has all of our y variables. Of course, these have to be the same number of rows because they're from the same set of data. And then we define a vector q that has all of the coefficients for our fit. And here, actually, I should have started this at 0, and gone to 1, and gone to n here. Okay. Once we have that written down, we can express our general model as A times Q equals Y, this matrix of processed X values times the vector of coefficients equals our target Y. These coefficients are the unknowns. They're the things that we don't know about the fit. We can find the coefficients for the minimum least squared error model, exactly the way that we did, using the pseudo-inverse. Q equals the pseudo-inverse of A times Y, where this pseudo-inverse is A transpose A all inverse multiplied by A transpose. So here we've wrapped up a discussion of the background, the conceptual ideas of projections, pseudo-inverses, least squares, solutions to inconsistent systems. In an accompanying worked example video, we'll go through examples of these. In another worked example video, we'll go through applications of using these projections. And in a subsequent lecture video, we will discuss extending ideas of orthogonality to find orthogonal bases, which makes all of this work of projections much, much easier. Thank you, and goodbye.